Today we're tackling some really fundamental building blocks of cloud computing. Think of this as a guided tour through your notes on AWS EC2 instances and the storage that goes with them, like EBS volumes.
That's right. And our goal here is to kind of synthesize all this, break down these sometimes complex ideas into, plain language, and hopefully highlight those connections, those aha moments that might be hiding in these concepts. We'll help you cut through the noise, get straight to what's impactful.
Exactly. So whether you're prepping for something specific, maybe an exam, or you're just curious and want to deepen your understanding, our mission is simple. We want to help you understand what these different pieces are, how they actually work together, and critically, why they matter in a real-world cloud environment. Okay, let's unpack this. Let's kick things off with something that sounds a bit different for a cloud server. EC2 Instance Hibernation. We usually think run or stop, right? What does hibernate even mean here?
Right. It's a good place to start because it's not the usual shutdown. Think of it more like hitting the pause button on your laptop, not turning it off completely. It's a freeze state. And the crucial difference, the really key thing from a regular stop, is what happens with the instance's memory. It's RAM. The source material is clear. The content in the RAM is actually saved.
Saved. Saved where?
It gets saved to the EBS root volume when you hibernate.
Whoa, okay, so it actually snapshots what's actively in memory. What else sticks around when you put an instance into this pause state?
Yeah, that memory state is the big deal because that's often what takes time to rebuild when you restart an application. Beyond that, the source confirms other essentials are preserved. You keep the instance ID, its unique tag. Any processes running right at that moment, they're frozen too. Your private IP addresses, IPv4, IPv6 if it had one, they stay. And importantly, the data on the EBS root volume itself, plus any other EBS data volumes you had attached, that all persists too.
Okay, preserving all that state. Why would you choose this instead of just stopping it? What's the killer use case?
The main reason highlighted in the source is what they call pre-warming applications. So if you've got software that takes a really long time to start up, maybe it loads huge data sets into memory or initializes complex caches, that kind of thing.
Yeah, some apps take forever.
Exactly. Stopping and restarting means you sit through that boot time every single time. Hibernation saves you all that. You start it back up and boom, it's right where you left off. It can shave minutes off getting ready.
Oh, okay. That speed angle makes a lot of sense for certain workloads. But what about the cost? Are you still paying for compute while it's just sitting there, paused?
Good question. It's an important cost difference. The source clarifies there's no billing when the instance is in stop hibernate state. That's for the instance compute itself. However, and this is key, you absolutely do still pay for the associated EBS volumes, where that RAM state and your data are stored.
Right.
And you also pay for any elastic IPs you might have attached. So you stop paying for the CPU and RAM cycles, but the storage costs definitely continue.
Got it. The storage has to persist that frozen state, so that makes sense. Okay, so from pausing instances, let's shift gears a bit. Where do these instances actually live within the AWS infrastructure? The source material talks about instances running on single-tenant hardware versus dedicated hosts. What's the core difference there, especially for just, the standard EC2 instances you launch?
Right. So the default EC2 instances, the ones you usually launch without special settings, they run on what AWS calls single-tenant hardware. Now, single-tenant here can be a bit misleading. It doesn't mean it's only your instance on that physical server. What it means is that while the underlying physical box might be shared, any other instances running on that same hardware also belong to the same AWS account as yours. That is, if they are also non-dedicated instances. The source is really clear that these default instances are not on dedicated hosts.
Okay. So think of it like maybe an apartment building. AWS is the landlord. I rent an apartment, by instance, and maybe other departments in my company rent other apartments in the same building.
That's a pretty good analogy, yeah. You have your own space, but others from your account might be in the same building.
So if the default is sharing hardware, but only within my account, what are dedicated hosts then? Are they totally separate?
Exactly. Dedicated hosts are different. That's when you actually pay for and get an entire physical server dedicated exclusively to your use. Nobody else's instances, not even from your own account unless you place them there. You get much more control over instance placement on that host. The source just touches on it briefly to contrast it with the default, mainly saying the default isn't that. The main takeaway for standard instances is you're paying hourly for compute on hardware that, while logically separate for you, might physically host multiple instances from your account.
Got it. Default is shared within the account. Okay. Now, once an instance is up and running, how does it find out information about itself from inside? That brings us to instance metadata, right? Yeah, the source mentions instance metadata and specifically points out two versions, IMDS v1 and IMDS v2. First off, what is instance metadata? Why would an instance need to know about itself?
Instance metadata is basically information about the running EC2 instance accessible from within that instance. Think of it like the instance's own digital ID card plus its current configuration details. You access it using a special local IP address 169.254.169.254. Applications or scripts running on the instance use this to discover things like its own instance ID, maybe public keys, network interface details, any user data you passed in at launch. And really critically, temporary AWS credentials if you're using IAM roles for EC2. That's a huge one.
Okay, so it's essential configuration and identity info. Right. Why the two versions then, V1 or V2? Is V2 just newer or is there more to it, like a security thing?
Oh, absolutely. Security is the key difference here, and it's probably the most important takeaway from the source on this topic. IMDS v1 works on a simple request response model. Your code makes a GET request to the metadata URL and it gets the data back. Straightforward.
Okay.
But IMDS v2 adds a really significant security layer. The source calls it session-oriented and protected by session authentication.
Session authentication. Does that mean you need like a password or a token first? You can't just ask for the data.
Exactly. With IMDS v2, the very first thing you have to do isn't asking for the metadata itself. You have to make a different request, usually a PUT request, to get a short-lived session token. The source describes this token kind of like a password for that specific session. You then have to include this token in the header of all your subsequent GET requests to actually retrieve the metadata values you want.
Ah, I see.
This session-based approach makes it much, much harder for certain types of attacks like server-side request forgery or SSRF to succeed. An attacker can't just trick your application into making a simple GET request to steal sensitive data like those IAM credentials. They'd need to be able to make that initial PUT request and grab the token first. It's a big security improvement.
That multi-step process sounds way more secure. Okay, good to know. Now, speaking of launching instances, we usually think on-demand, but there are other ways to buy and manage them, especially if you're looking for cost savings. Right? On-demand is the standard pay by the hour, but the source digs into Spot Fleet and the newer EC2 fleet. How do these fit in? Are they just for Spot instances?
Well, they're definitely often used with Spot instances, but they're broader than that. They are services designed to help you launch and manage a collection or fleet of EC2 instances based on a single configuration request. It's about managing capacity efficiently, often mixing instance types or purchase options, and yes, frequently leveraging those discounted Spot instances, which are AWS's spare compute capacity.
Okay, collections of instances. And what's the relationship between Spot Fleet and EC2 fleet? Is one just an update of the other?
Pretty much. The source gives us the dates. Spot Fleet came first, May 2015. Then EC2 Fleet arrived in May 2018. And it explicitly calls EC2 Fleet an evolution of Spot Fleet. So yeah, EC2 Fleet is the more modern, more capable version.
And how do they differ in what they launch by default, if I just set one up simply?
That's actually a pretty notable difference, according to the source. Spot Fleet, maybe not surprisingly given the name, defaults to launching Spot instances. EC2 Fleet, on the other hand, defaults to launching on-demand instances. It can absolutely launch Spot instances too, or a mix, but its default starting point is on-demand.
Huh, interesting. EC2 Fleet defaults to the more expensive option initially. How do their features compare side by side based on that table in your source material?
They do share some core abilities. Both can use launch templates. That's the standard way to define your instance config now. Both can launch a mix of on-demand and Spot instances within the same fleet request, which is great for balancing cost and availability. And both can automatically use any matching reserved instance pricing you might have, helping you maximize savings if you have RIs.
Okay, so they can both mix and match. Any other key differences that stand out from the source?
Yeah, a few important ones for EC2 Fleet. It can reference an on-demand capacity reservation ID, which Spot Fleet cannot. This lets you guarantee on-demand capacity within the fleet. Both let you set a maximum price you're willing to pay for the fleet per hour. EC2 Fleet supports more ways to manage the request lifecycle. It has a one-time synchronous option, a standard asynchronous request type, and a maintain type to keep capacity up. Spot Fleet just has request and maintain. And there's a little note in the source saying Spot Fleet can be configured from the AWS console, but apparently EC2 Fleet cannot. You'd use the API or CLI. That might have changed since the source was written, but it's worth noting.
Okay, so EC2 Fleet seems like the way to go. Generally newer, more flexible, handles capacity reservations. But that console limitation is interesting. Now, the big catch with Spot, as we mentioned, is interruption. How does AWS handle taking that capacity back? Yeah, the potential for interruption is the price you pay, literally, for the spot discount. What's the standard default behavior? What happens when AWS needs that instance back?
The source is blunt. The default behavior for a spot instance interruption is terminating the instance. Just gone. Poof.
Ouch. Okay, terminate is harsh. That won't work for everything. Is there any way to avoid just having it deleted?
Yes, thankfully, but with a couple of caveats. It needs to be an EBS-backed spot instance, and the instance type needs to support it. If those conditions are met, you can change the interruption behavior from the default terminate to either stop or hibernate.
Oh, stop or hibernate.
Right. Choosing stop means the instance is shut down cleanly, the EBS volumes persist, but it's not deleted. You can start it again later when capacity is available. Choosing hibernate, like we discussed earlier, saves the RAM state to EBS. So when you restart it, it picks up exactly where it left off. Fantastic for those long starting apps, but again, only if supported.
Does AWS give you any warning before they just terminate, stop, or hibernate it?
Yes, the standard procedure is a 2-minute warning. AWS sends a signal, usually via the Instance Metadata Service, or you can catch it with EventBridge, giving you 120 seconds notice before the interruption actually happens. Enough time for some cleanup, maybe.
2 minutes isn't a lot, but it's something. Now, what's this spot instance rebalance recommendation the source talks about? That sounds like maybe more warning.
It is, and this is one of those really valuable features for making Spot more usable for serious workloads. It's an earlier signal. It comes before the 2-minute warning. AWS sends this signal, again via EventBridge usually, when an instance is merely at an elevated risk of interruption. They haven't decided to take it back yet, but the underlying capacity pool is getting tight, suggesting it might happen soon.
Why is getting that earlier signal so useful? What can you do with it?
It gives you significantly more time to react proactively. Instead of scrambling in the last 120 seconds, you get this heads up potentially minutes earlier. You can set up automation using EventBridge to trigger actions when this recommendation comes in. The source highlights that auto-scaling groups, EC2 fleet or spot fleet, can be configured to automatically launch replacement spot instances when the signal is received. So you start replacing the at-risk instance before it even gets the 2-minute termination notice. It's a way to proactively maintain your desired capacity and gracefully handle potential interruptions. It's a real game changer for spot reliability.
Wow, that rebalance recommendation sounds crucial for anyone serious about using spot for anything stateful or long-running. Okay, so we've got instances, we manage interruptions. Now, where do we actually place them physically within AWS if they need to talk to each other really fast? The source brings up placement groups and specifically mentions partition groups. Broadly speaking, what problem are placement groups trying to solve?
Placement groups are all about giving you more control over the physical placement of your EC2 instances within an AWS data center or across availability zones. You use them primarily to influence network performance between instances or to improve the fault tolerance of your application.
Okay, controlling location. The source seems to start by emphasizing putting instances in a single AZ for certain scenarios. Why would you deliberately choose not to spread things out? Seems counterintuitive for the cloud.
It does seem that way, but there's a specific reason: achieving low node-to-node latency. If you have an application, often high-performance computing or HPC workloads, where instances need to communicate with each other extremely quickly with minimal network delay, putting them close together in a single AZ within a cluster placement group is the best way. The source does note the trade-off clearly. This single AZ has a huge cost advantage compared to multi-AZ setup sometimes, but the big risk is indeed no high availability. If that single AZ has issues, your whole cluster is affected.
Okay, so single AZ placement is purely for speed demons, where latency is everything. What about the partition placement groups then? How do they work, and what's their goal?
Partition placement groups aim for distribution and fault isolation. When you use one, AWS launches your instances into different logical partitions, end quote. The source explains that each partition represents a distinct set of underlying hardware specifically. It says each partition is on a separate rack. You can define how many partitions you want, up to 7 per AZ, and these groups can span one or more availability zones, AZs, in one region.
Separate racks, potentially across AZs.
Yeah.
What kind of applications benefit from being spread out like that?
The source gives some great examples. Distributed systems like HDFS, Hadoop Distributed File System, HBase, and Cassandra Database. These are systems designed from the ground up to handle data spread across many nodes. They expect nodes to fail occasionally, so placing their nodes on separate racks using a partition group aligns perfectly with their architecture. If one rack fails, it only impacts the instances in that partition, and the distributed system itself can usually handle that failure gracefully. It improves fault isolation.
Got it. Cluster for speed, partition for spreading out fault-tolerant systems. That makes sense. Now, once these instances are running, however they're placed, how do you keep tabs on their health and performance? Monitoring is absolutely essential, right? And AWS CloudWatch is the go-to service. But the source points out a really common pitfall regarding the metrics you get by default.
Yes, and this is a big one. You really need to internalize this. The source literally warns, pay attention to what is not sent by default to CloudWatch.
So what are some of those crucial metrics that you don't get automatically? The ones you might assume are there?
The source explicitly calls out memory utilization and disk space utilization. It flags these as key metrics required for monitoring, but crucially, they are not sent by default. This catches so many people out. You launch an instance, you look at CloudWatch, you see CPU, you see network, but you have no idea how much RAM your app is actually using, or if the root disk is about to fill up, unless you do something extra.
Okay, so if I need to know memory usage or disk space, how do I get those metrics into CloudWatch?
You need to use what AWS calls custom metrics, and to get those custom metrics, the source states it requires the CloudWatch agent. This is a piece of software you have to install, configure on your EC2 instances. The agent then collects these additional data points locally and pushes them up to CloudWatch for you.
Can you just quickly summarize that split again? What is default versus what needs that agent, based on the source list?
Sure. Based on the source list, default metrics, the ones you get automatically, include things like CPU utilization, network utilization, bytes in, out, and basic disk performance metrics, read-write operations, read-write bytes. Custom metrics, the ones requiring the CloudWatch agent, include memory utilization, disk swap utilization, disk space utilization, like percentage used, and page file utilization on Windows. So, bottom line. If memory usage or disk free space is important for your application's health or scaling, you absolutely need that CloudWatch agent installed and configured.
That's a super important distinction. Easy to get tripped up there. Okay, let's shift focus slightly to the underlying tech that makes a lot of the newer, faster instances possible. The source mentions the Nitro system. It says Nitro-based instances provide higher performance. What actually is the Nitro system?
The Nitro system is AWS's modern underlying platform. It's a combination of dedicated hardware and a specialized lightweight hypervisor that powers most current generation EC2 instances. The key benefit, and the source highlights this, is that it delivers practically all the compute and memory resources of the host to the hosted EC2 instances.
How does it manage that? Does it sort of get out of the way more than older systems?
That's a great way to put it. Traditionally, the hypervisor software itself consumes some of the host server's CPU and RAM to do its job managing virtualization, networking, storage access, security functions. Nitro basically offloads most of those functions onto dedicated hardware cards and security chips. The Nitro cards handle things like VPC networking and EBS storage access. This frees up the main host CPU and memory, making almost all of it available directly to your EC2 instance and your workload. And the result, as the source notes, is that Nitro-based instances can provide higher speed networking, higher speed EBS volumes, and higher IOPS. It's a significant performance boost across the board.
That offloading makes a lot of sense for squeezing out performance. And it leads us perfectly into talking more about those EBS volumes, the main persistent storage for EC2. Right, EBS. The source gives a really helpful breakdown of the different EBS volume types, splitting them into two main camps, SSD-based and HDD-based. Let's start with the SSDs. What types fall under that umbrella?
Under the SSD category, the source lists two main families: general purpose, which includes GP2 and the newer GP3, and provisioned IOPS, covering IO1, IO2, and the very high-end IO2 Block Express.
Okay, general purpose GP2 and GP3. What kind of jobs are they good for, and what are their main characteristics?
General purpose volumes are really the workhorses for a huge range of common workloads. Think general applications, smaller databases, dev test environments, virtual desktops, boot volumes. Their performance is primarily measured and balanced around IOPS, input-output operations per second. Cost-wise, they're higher than the HDD options, naturally. The source emphasizes they're good for random IOs and consistent performance, which is typical of many application access patterns. GP3 is generally preferred now as it lets you provision IOPS and throughput independently of size, offering better performance costs usually.
Makes sense. Workhorse SSD. What about the provisioned IOPS types, IO1, IO2, IO2 Block Express? What makes them different? Why pay more for them?
These are designed for your most demanding applications. We're talking large IOPS-intensive workloads that require consistent performance. Think large production databases, relational or NoSQL, that need guaranteed high levels of IOPS. They are also IOPS-oriented, but they come at the highest cost among the types listed. The trade-off is they deliver potentially large or extremely high IOPS per volume, way beyond what general purpose offers, especially IO2 Block Express. Again, the focus is random IOs and consistent performance, but at a scale and guaranteed level needed for critical high-throughput applications.
Okay, highest performance, highest cost for those critical databases.
Yeah.
Now, shifting gears to the HDD-based volumes, what types does the source mention there?
For hard disk drives, the source lists two types: throughput optimized, which is ST1, and cold HDD, which is SC1.
Tell us about throughput optimized, ST1. What's its niche?
These are all about large sequential I/O workloads. The key word there is sequential. Think big data processing jobs using tools like Amazon EMR, ETL processes, data warehousing, large-scale log processing. Also good for streaming workloads requiring consistent fast throughput at a low price. Their performance metric isn't IOPS, it's throughput measured in megabytes per second, MBs. They offer low cost compared to SSDs. The source really hammers this home for large sequential IOs, throughput-based, think HDD-based EBS storage.
Got it. Sequential reads writes, throughput matters, cost is lower. And the other HDD type, cold HDD, SE1.
Cold HDD SE1 takes the cost focus even further. These are for large sequential cold data workloads, data that's infrequently accessed but still needs to be stored cheaply. They're also throughput-oriented for when you do access the data, again, sequentially, but they offer the absolute lowest cost per gigabyte of all the EBS types listed. Use these when minimizing storage cost is the most important factor, and you primarily do large sequential reads when you access the data at all.
Okay, so the fundamental split seems pretty clear from the source. SSDs for random I/O patterns where IOPS and consistent low latency matter most. HDDs for large sequential I/O patterns where throughput is the main performance metric, and cost is often a bigger driver.
Exactly. Matching the volume type to your application's specific access pattern and performance needs is absolutely critical for both getting the performance you need and not overspending on storage.
Beyond just picking the right type, EBS has some interesting extra features. Let's touch on EBS multi-attach. What exactly does that let you do?
EBS multi-attach is a pretty neat feature. It allows a single EBS volume to be attached to multiple EC2 instances at the same time, concurrently.
Whoa, okay. Multiple instances accessing the same block device. That sounds useful for maybe clustered applications or something needing shared storage. Are there limits mentioned? Which volumes support it?
Yeah, it definitely has specific use cases, often around clusters needing shared block access, but there are very clear limitations mentioned in the source. It's supported exclusively on provisioned IOPS, IO1 or IO2, EBS volumes, so only the high-performance, higher-cost SSD types, and it can only attach to up to 16 Nitro-based instances in the same AZ, so you need Nitro generation instances, and all those instances and the volume must reside within the same single availability zone. It's also important to remember this provides shared block access. It doesn't automatically make it a shared file system. Your application or a cluster-aware file system running on the instances needs to be able to manage concurrent block access safely.
Okay, very specific requirements. PIOPS volumes, Nitro instances, single AZ, and application awareness. Good to know the constraints. Now, what about encryption for EBS volumes? How does that work? Is it secure?
EBS encryption is a standard and crucial security feature. The source explains that the encryption happens on the host of the EC2 instance, meaning the physical server where your EC2 instance is running encrypts the data before it's written out to the EBS volume storage infrastructure.
So the data is encrypted before it even leaves the EC2 host server and travels over the network to the actual EBS storage system.
Exactly. The source confirms this. Data in transit to an encrypted EBS volume is also encrypted. The encryption and decryption are handled transparently by the EC2 host using keys usually managed by AWS Key Management Service, KMS.
Can you decide to encrypt a volume after you've already created it as unencrypted? Or vice versa?
No, the source is quite firm on this. We cannot change the encryption status of an encrypted volume. Once an EBS volume is created, its encryption state, whether it's encrypted or unencrypted, is fixed for its lifetime.
Okay. Fixed state. But what if? What if I have data on an encrypted volume, and for some valid reason I absolutely need that same data on an unencrypted volume? Is there any way to effectively unencrypt it even indirectly?
Yes, the source describes a workaround. It's not a direct toggle, but a migration process. You would need to mount a second unencrypted volume to the same instance that the encrypted volume is attached to. Then, from within the instance's operating system, you'd copy migrate the data from the encrypted volume to the unencrypted volume using standard file copy tools like rsync or robocopy. Once the data is safely copied, you could detach and delete the original encrypted volume if you no longer need it. So it involves an intermediate instance and a data copy.
Got it. A manual copy process via an instance. Good to know there's a path, even if it's not a simple switch. Okay, besides these persistent EBS volumes, there's another flavor of storage tied directly to some instances, right? Instant store. What's the fundamental difference between an EBS volume network attached, persistent, and an EC2 instant store volume?
The core differences are location and lifespan. Instant store volumes provide temporary block storage. They are physically located on the same host machine that your EC2 instance is running on. They aren't network attached like EBS. And the key word here is temporary. The source stresses that data persists only during the lifetime of the instance. If you stop, hibernate, or terminate the instance, poof, any data on the instant store volumes associated with it is gone, permanently lost.
Yikes. Okay, temporary is putting it mildly. Data loss on stop terminate sounds pretty risky. What are they actually good for then if the data just vanishes?
They're ideal for exactly that. Temporary storage of data that changes frequently, or data that doesn't need to persist if the instance restarts. The source gives examples like using them for buffers and caches, scratch data like temporary files during complex calculations, or temporary content like maybe intermediate files during video transcoding. Basically, any data where you prioritize extremely high speed and low latency while the instance is running, and you either don't care if it's lost on termination or your application can easily regenerate it.
Are these instant store volumes something you add on, like EBS, or do they come with certain instances?
They typically come with specific instance types. You don't usually attach them separately like EBS. The source gives examples like the i3 and i3N instance families, which are specifically designed for I/O-intensive workloads and come equipped with fast, often NVMe-based instant store volumes.
And the source mentions they can provide millions of IOPS. It's incredibly fast, right? Much faster than EBS.
Oh yeah, they can be significantly faster than EBS for certain access patterns, especially regarding latency, because the storage is physically local to the instance's host server. No network hop involved. That's why, despite being temporary, they're sometimes used for things like high IOPS, OLTP databases, relational DBs, and non-relational DBs, specifically for temporary table spaces, caching layers, or workloads where the absolute lowest latency is critical and data persistence is handled elsewhere, like replication or EBS logs.
Okay, so mind-blowing performance for the right use case, but you absolutely have to understand and design around the fact that the data is ephemeral. Got it. Now, speaking of storage architectures, let's look at combining multiple EBS volumes using RAID. The source briefly touches on using RAID redundant array of independent disks, but specifically with EBS volumes. What's the basic concept? Why would I want to combine multiple EBS volumes this way?
The idea behind using RAID with EBS is to take several individual EBS volumes and have the operating system on your EC2 instance treat them as a single larger logical volume. You typically do this for one of two main reasons, or sometimes both, to aggregate performance, get higher IOPS or throughput than a single volume could provide, or to add data redundancy, protect against the failure of a single EBS volume.
Okay, let's break down the types mentioned. First, RAID 0, often called striping. What does that configuration do?
RAID 0 stripes data across all the volumes in the array. When your OS writes a chunk of data, it breaks it into smaller pieces and writes those pieces simultaneously across the different volumes. This combines volumes for increased IOPS throughput. The source notes the performance gain clearly. The resulting IOPS is the sum of individual IOPS for all volumes. So 2 volumes roughly double the IOPS throughput, 3 volumes triple it, and so on. But, and this is a huge, but there is no redundancy mirroring. The source explicitly warns, failure of any volume means failure of the entire array. If one EBS volume in your RAID 0 set fails or gets corrupted, all the data on the entire logical volume is lost. High performance, zero fault tolerance.
Ooh, okay. RAID 0 for maximum speed, but super risky. What about the opposite end, RAID 1, known as mirroring?
RAID 1 does exactly what the name implies. It mirrors data. Every time your OS writes data to the logical volume, the exact same data is written identically to all the physical EBS volumes in the array. Usually, you'd use 2 volumes for RAID 1. This provides no IOPS performance enhancement for writes because you still have to write the data to both volumes. Read performance might sometimes be slightly better, but don't count on it. The huge benefit is improved fault tolerance and data protection. It's redundant. If one of the EBS volumes fails, the other one still has a complete identical copy of the data, and your application can continue running uninterrupted using the remaining volume. Protection is the priority here.
Got it. Protection over performance for RAID 1. What about the last one mentioned, RAID 10, sometimes called RAID 1 plus 0?
RAID 10 tries to give you the best of both worlds. It combines the benefits of RAID 0 and RAID 1. How it works is by striping data across mirrored pairs of EBS volumes. So you start with pairs of volumes, where each pair is a mirror, RAID 1. Then you take these mirrored pairs and stripe the data across them, RAID 0. This setup provides redundancy because of the mirroring and performance enhancements because of the striping across pairs. The catch is the requirement. You need a minimum 4 volumes to even start 2 volumes for the first mirror, 2 for the second, then you stripe across those 2 pairs. It offers a good balance, but needs more underlying volumes.
Right, so RAID 0 for speed, RAID 1 for safety, RAID 10 for a mix of both, but needs more drives. That clarifies the options nicely. Okay, moving away from structuring active storage, let's talk about backups and recovery using EBS snapshots. EBS snapshots seem pretty fundamental for backing up data on AWS. What exactly is an EBS snapshot?
Yep, they're the standard way to back up EBS volumes. An EBS snapshot is essentially a point-in-time copy of your EBS volumes data. The source highlights a couple of key things about them. They are a regional resource, meaning a snapshot exists within the specific AWS region where it was created. And under the hood, snapshots are saved on S3 and are encrypted at rest by default for security and durability, even though you manage them via the EC2 EBS interface, not S3 directly.
Okay, point-in-time backup, stored regionally on S3 infrastructure. What if I need that backup in a different AWS region, maybe for disaster recovery or launching services elsewhere?
Good question. Since they're regional, you can't use a snapshot directly in another region, but you absolutely can copy the snapshot to that region. AWS provides a function to copy snapshots between regions. Once the copy completes in the target region, you can then use it there, for instance, to create a new EBS volume from it.
And the source lists some common reasons for doing that cross-region copy, right?
Exactly. The key use cases mentioned are geographic expansion, setting up your service in a new part of the world. Disaster recovery, having backups ready in a separate region in case your primary region has a major issue. Migration to another region, moving your workload permanently. And also for data retention and compliance audit requirements that might mandate storing backups geographically distant from the primary data.
Makes sense. What about encryption when copying snapshots? If my original snapshot was encrypted, can I copy it?
Yes, you can definitely copy encrypted snapshots. However, there's an important detail if you're copying it to a different region. The source notes that AWS will enforce changing the encryption key to a key in the new region during the process. This means you'll typically specify a KMS key in the destination region to re-encrypt the snapshot data as it's copied. You can't just copy the snapshot encrypted with a key from the source region. It ensures keys are managed regionally.
Okay, re-encryption with a local key on cross-region copies. Can you directly unencrypt an encrypted snapshot, like make an unencrypted copy from an encrypted one?
No, similar to volumes, you can't directly change the encryption status of the snapshot itself. However, the source notes a useful capability in the other direction. You can directly create an encrypted volume from an unencrypted snapshot during the volume creation step. To effectively unencrypt data from an encrypted snapshot, the workaround is usually restore the encrypted snapshot to a new EBS volume, making sure to not select encryption for this new volume if your account settings allow unencrypted volumes. Then you could take a new unencrypted snapshot of that volume if needed.
Got it. Again, it's often about restoring to a volume, potentially changing the encryption state during that step, and then maybe snapshotting again. Managing all these snapshots, manually creating them, deleting old ones sounds like it could become a real chore. Yeah, how do you automate that?
Yeah, manually remembering to take snapshots daily, weekly, and then cleaning up the old ones. That sounds like a recipe for mistakes, or just a lot of work. The source mentions EBS snapshot lifecycle policies and Amazon Data Lifecycle Management, DLM. What does DLM do for you? Amazon Data Lifecycle Manager, or DLM, is specifically designed to solve that exact problem. The source calls it a total solution for creating, deleting, and retaining EBS volume snapshots. It's AWS's way to automate your snapshot management.
How does it actually work? How do you set it up?
You configure snapshot lifecycle policies within the DLM service. In these policies, you define rules. You specify which EBS volumes the policy should apply to, usually by targeting volumes with specific tags, like environment, production, or backup, daily. Then you define the schedule how often to create snapshots, gradually every 12 hours, daily at 2 a.m. And crucially, you define the retention rules how long to keep them. E.g., keep daily snapshots for 7 days, keep weekly snapshots for 4 weeks, keep monthly snapshots for a year. A single policy can manage snapshots for a single volume or multiple volumes attached to an instance based on those tags.
So DLN just handles the scheduling, the creation, and the automatic deletion of old snapshots based on the rules you set.
Precisely. Set it up once, and it takes care of the entire lifecycle.
Huh.
It massively simplifies backup management.
Okay, DLM sounds essential. But what if, despite automation, someone accidentally deletes a really important snapshot? Or maybe even deletes an AMI that depended on snapshots. Is there any kind of safety net, like an undo button?
There is. It's not quite undo, but it's close. That's where the recycle bin feature comes in. The source describes it as a data recovery feature of EC2, specifically designed as a safety net for accidentally deleted snapshots or EBS-backed AMIs.
Oh, interesting. How does the recycle bin actually work?
When you configure recycle bin rules for your account or region, any snapshots or AMIs deleted that match the rule don't get permanently deleted immediately. Instead, they're moved into the recycle bin and retained in the recycle bin for a period of time. You get to decide on this time period using retention rule that you configure, maybe 7 days, 30 days, whatever makes sense for you. During that retention period, you have the option to go into the recycle bin and recover the resource if you realize the deletion was a mistake. Only after that defined retention period expires are the resources permanently deleted.
That sounds incredibly useful for catching mistakes. Are you charged for the storage of those snapshots or AMIs while they're sitting in the recycle bin?
Yes, that's a critical point. The source notes. Resources in the recycle bin are charged the normal snapshot charges, so it's a fantastic safety net, but it's not free. You're paying for that recoverable storage just like you would for a regular snapshot.
Good to know. The safety net has a cost, but probably worth it in many cases.
Yeah.
Okay, so from snapshots, volume backups, let's look at Amazon machine images, which are more like templates for launching whole instances, right? AMIs, they're the templates you select when you launch a new EC2 instance. The source talks about creating your own customized AMIs, often called golden AMIs. What's the main idea or benefit behind doing that?
The core idea is standardization and efficiency. You start with the base AMI provided by AWS or the marketplace. Then you launch an instance from it and customize it. This means installing your standard operating system patches, maybe your company's required monitoring or security agents, common software libraries your applications need, maybe even pre-deploying your application code. Once that instance is configured exactly how you want all your instances to start, you create your own customized approved AMI, golden AMI, from that running instance. The benefit is huge. Every time you launch an instance from that golden AMI, it already has all your standard configurations baked in. It saves immense amounts of time during instance boot and ensures consistency across your fleet.
Okay, so it bundles up your customizations. What technically gets included in that custom AMI package?
When you create an AMI from an instance, it primarily includes snapshots of all attached EBS volumes that were part of that instance configuration, typically the root volume, and any data volumes you had attached and configured to be part of the AMI. And just like regular snapshots, these underlying AMI snapshots are stored in S3 for durability, managed via the AMI interface.
Can you copy these golden AMIs, say, to use them in a different AWS region, or maybe share them with another team in a different AWS account?
Yes, absolutely. The source confirms we can copy an AMI within the same account in the same region or across AWS regions. Copying to other regions is common for geographic expansion, or DR, similar to snapshots.
What if my golden AMI was built from an instance that used encrypted EBS volumes? Can I still copy that AMI?
Yes, we can copy AMIs with encrypted snapshots. However, just like with standalone snapshots, if you're copying an encrypted AMI to a different region, the source notes that AWS will enforce changing the encryption key to a key in the new region during the process. You'll need to specify a KMS key in the destination region for re-encryption.
Okay, similar key management applies. What about sharing AMIs with completely different AWS accounts? Maybe a partner account or a subsidiary?
Sharing AMIs between accounts is also possible, and the source mentions a lab on this topic. If the AMI uses encrypted snapshots, the sharing process gets a bit more complex. It depends on the KMS keys used to encrypt those volume snapshots. You, the owner of the AMI and the keys, need to explicitly grant permission to the other account to use those specific KMS keys. Without key permissions, they can't launch instances from the shared encrypted AMI. And the source clarifies a really important cost and ownership point. Sharing an AMI does not change its ownership. The owning account is charged for the storage of the AMI. So even if hundreds of other accounts launch instances from your shared AMI, you still pay for storing that base AMI and its snapshots.
Ah, owner pays for storage. Good to know. Are there any types of AMIs that are particularly difficult or even impossible to copy or share directly between accounts?
Yes, the source points out a couple of key limitations. AMIs from the marketplace, with billing product codes. Think commercial software AMIs you pay for, and also standard Windows AMIs generally can't be copied to another account directly. This is usually tied to the licensing agreements and billing mechanisms associated with those specific AMIs.
Okay, Marketplace and Windows AMIs have restrictions. Is there a way around that if you really need to get an instance based on one of those into another account?
Yes, the source provides a common and effective workaround. To work around that, launch an instance from the AMI in the original account, then create an AMI from that EC2 instance, but initiate the creation from the target account, often by sharing the instance temporarily or using automation. This process effectively creates a brand new custom AMI in the target account that captures the state of the running instance. But this new AMI isn't tied to the original marketplace product code or Windows license in the same way, bypassing the direct copy restriction.
Clever. Launch, then recaptures a new AMI in the target account. That's a really practical tip. Okay, we've covered a ton on instances, storage, backups, templates. Let's quickly touch on a few other related AWS services mentioned in your source material that build on these core concepts. Right? The sources also mentioned a few other services that interact with or build upon EC2 and EBS. Let's start with AWS Batch. What's that service for?
AWS Batch is described as a fully managed regional service that simplifies running batch jobs of any scale. It's designed specifically for running large volumes of computing tasks that don't require real-time user interaction.
What qualifies as a batch job in this context?
The source defines it as a data processing task that will run without user interaction. Often these are background processes, maybe scheduled usually after working hours. Classic examples given are things like end-of-day billing, payroll, data conversion, but also things like large-scale image processing, inventory processing, report generation. The source also lists more computationally intensive use cases like digital media rendering, drug screening, and post-trade analysis in finance.
Okay, background processing tasks. How does AWS Batch actually simplify running them? What's the value?
The big value proposition is that customers do not have to run or maintain servers or schedulers themselves. You define your batch job, usually as a Docker container, specify its resource requirements, CPU, memory, and submit it to a queue in AWS Batch. AWS Batch then plans, schedules, and executes the batch computing workloads. Critically, it also provisions the optimal quantity of compute required, automatically launching and managing EC2 instances, often spot instances for cost savings to run your jobs, and scaling the fleet up or down based on the queue depth. It can handle huge scale. And the source notes a nice cost aspect. There is no additional charge for AWS Batch itself. You just pay for the underlying AWS resources it consumes, like the EC2 instances and EBS volumes it uses to run your jobs.
Okay, managed compute for batch processing. Next up, AWS Outposts. This sounds different, like bringing AWS out of the AWS region.
That's exactly what it is. AWS Outposts is a fully managed service that extends AWS infrastructure, services, APIs, and tools to the customer on-premises location.
So you mean actual AWS hardware sitting in my own data center or co-location facility?
Precisely. It's delivered as a pool of AWS compute and storage capacity deployed at a customer site. It could be Outposts 1U2U servers or one or more full Outposts racks filled with AWS design hardware. The key is that AWS operates, monitors, and manages this capacity as part of an AWS region. You interact with it using the same console, APIs, and tools you use for the public AWS regions. This lets you run applications on premises that need very low latency access to local systems or data or have data residency requirements, but you still get that consistent AWS operational experience and API interface.
What kind of AWS services can you actually run on that Outpost hardware locally?
It effectively extends the AWS VPC to the on-premises location. You can run core services like EC2 instances, use EBS block storage locally on the Outpost, run container services like ECS or EKS, use RDS for databases, run local S3 storage, S3 on Outposts, and various others. It connects back securely to the parent AWS region for management and access to regional services not available locally on the Outpost itself.
Interesting. Bringing the cloud operating model on-prem. The source also mentions Amazon Lightsail. How does that compare or fit in with standard EC2?
Amazon Lightsail is positioned as a much simpler, easier-to-use service, primarily aimed at developers or users who want to build websites or web applications with low-cost, pre-configured cloud resources.
What do you get with Lightsail? Is it just a VM?
It's more of a bundled package. When you choose a light sale plan, you get a virtual private server, an instance. But the plan typically includes a set amount of SSD storage, a data transfer allowance, DNS management capabilities, a static IP address, and even options for managed databases, load balancers, CDN integration, and snapshots backups. It bundles all the common pieces needed for simple web apps into easy-to-understand, fixed monthly price plans. It abstracts away a lot of the individual configuration steps you do with EC2, VPC, EBS, Route 53, etc. Much simpler entry point.
Okay, simplified bundle for web apps. And finally, VMware Cloud on AWS. The name sounds pretty self-explanatory, combining VMware with AWS.
That's exactly it. VMC on AWS allows customers who are already heavily invested in VMware's virtualization platform, vSphere, in their own data centers to launch or migrate their vSphere-based workloads, VMware SDDCs, in AWS.
So they can run their familiar VMware environment, but on AWS hardware. What kind of hardware?
Yes, they run the complete VMware software-defined data center, SDDC stack, vSphere, VSN, NSX, but it runs on dedicated, powerful EC2 bare metal instances within an AWS data center. The source specifically mentions it uses i3N got metal instances on AWS as the underlying hardware hosts.
How does that VMware environment running inside AWS talk to other native AWS services like S3 or Lambda or regular EC2 instances?
The source explains there's a high-speed connection setup. The VMware SDDC can communicate with the native AWS services, EC2, ODS, etc., through an ENI Elastic Network Interface deployed in the customer's VPC. This creates a low-latency bridge, allowing VMs running inside the VMware environment on AWS to access services running in your regular AWS VPC, and also public AWS service endpoints like S3, DynamoDB, Lambda, etc. It enables hybrid architectures, mixing VMware and native AWS capabilities.
Wow, okay. So we really covered a huge amount of ground there. From the basics of pausing instances with Hibernation to choosing the right storage, backing it up, templating deployments, and even extending or integrating with other platforms. It's quite a journey we took. We navigated through hibernation states for those quick application starts, understood how default EC2 instances might share hardware within your account versus dedicated options, definitely secured our instance metadata access using IMDS v2.
Right, and looked at smart ways to buy and manage capacity with EC2 Fleet and Spot, plus mitigating spot interruptions with that rebalance recommendation and stuff hibernate behaviors.
We saw how to carefully place workloads using cluster groups for speed or partition groups for fault tolerance. Made sure we know how to really monitor instance health by getting those custom metrics like memory and disk space with the CloudWatch agent.
Appreciated the performance boost from the Nitro system, dug deep into the trade-offs of all those different SSD and HDD EBS volume types, GP3, IO2, ST1, SC1.
Learned how to combine volumes with RAID 0, 1, or 10 for different goals, how EBS encryption works, and those tricky workarounds for changing encryption state. Understood the role of super fast but temporary instance store.
Automated our backups with DLM, added that safety net with the recycle bin, standardized deployments using golden AMIs, and figured out the rules for copying and sharing them, even the tricky marketplace and Windows ones.
And finally touched on specialized services like Batch for processing, Outpost for bringing AWS on-prem, Lightsail for simplifying web stuff, and VMC on AWS for bridging the VMware world. Whew.
It really does underscore the sheer range of options AWS provides, doesn't it? Each piece has its own specific characteristics, ideal use cases, and importantly, trade-offs you need to consider: cost, performance, resilience, ease of use, management overhead. Understanding these fundamentals, how these building blocks fit together, is just absolutely essential for designing and running effective, efficient solutions in the cloud.
Absolutely. And here's where it gets really interesting for you, the listener. Thinking about all these components we've unpacked, maybe combining hibernation for fast restarts with spot instances managed by EC2 Fleet, using the rebalance recommendation for cost-effective stateful tasks.
Or perhaps leveraging high-performance Nitro instances with IO2 multi-attach EBS volumes for a specific kind of clustered database. Maybe even thinking about when RAID 0 on Instance Store makes sense for scratch space versus RAID 1 on EBS for critical data.
How might combining just 2 or 3 of these tools or techniques, maybe in a way you hadn't considered before, unlock new possibilities, efficiencies, or resilience for a project you're working on right now? What specific combination stands out to you from today's discussion as something worth exploring further in your own environment? That wraps up our deep dive into this material. Thank you for joining us today.